Space seems empty until physics asks a quieter question. What does empty mean? If clocks slow down, light sets the boundary of cause and effect, and gravity can bend the very measure of distance and time. In this journey, space-time is not treated as a confusing abstraction, but as the hidden order behind motion, black holes, expanding galaxies, and the ticking of every clock. If calm, thoughtful science journeys like this are valuable, a gentle like, subscribe, or share helps calm space science keep creating them. Thank you for spending part of your time here. Wherever this video finds you, leave a comment with your city or country, what time it is there, and whether this is playing while studying, relaxing, or drifting towards sleep. The path now begins with the simplest question, space itself, and slowly follows it toward the unfinished edge of modern physics. Space is often treated as the simplest part of reality, because it seems to be the place where everything else appears. A planet has a position, a star has a distance, a hand can move from one side of a table to the other. In everyday life, space feels like the quiet container around objects, present before anything happens and still present after motion ends. Yet physics does not use space only as empty room. It treats space as a structure of measurable relations. It is the order that allows one event to be near another, one direction to differ from another, and one path to have a length while another path is shorter. Without this structure, there would be no clear meaning to location, no way to compare distances, and no stable language for motion. Space is not simply the absence of matter. It is the framework through which matter can be arranged, separated, connected, and described. That difference matters because the first step toward understanding space-time is recognizing that space is already more than a blank background. In older common sense, space can seem independent of everything inside it. Remove the planets, remove the gas, remove the light, and some silent extension seems to remain. This view is close to the picture that guided much of classical physics. Space could be imagined as a fixed stage, with objects placed upon it and motions performed across it. The stage itself did not bend, flow, or respond. It supplied position and distance, but did not take part in the action. This picture works extremely well for ordinary speeds, ordinary distances, and ordinary gravitational fields. A stone thrown through the air, a wheel turning on a road, or a ship crossing an ocean can be described with space acting as a stable background. Measurements made in this way are not false. They're practical and deeply successful within the limits of daily experience. But the success of a practical picture can hide the deeper question. If space is the system that allows distance and direction to exist, then physics has to ask what kind of system it is. To measure space, there must be coordinates. A coordinate is a way of assigning ordered values to positions, so that one location can be distinguished from another. On a flat map, two values may be enough. One can mark how far east or west a point lies, and how far north or south it lies. In the physical world, a third spatial value is needed, because objects can also lie above or below one another. These three spatial directions are not special, because nature prints labels on them. They're useful because movement in one direction can be separated from movement in the others, and because together they can identify where something is. A spacecraft near Mars, a grain of dust in a laboratory, and a galaxy in a survey can all be given positions only because space supports this kind of ordering. The coordinate grid is not space itself. It is a human method for describing the relations that space makes possible. A different observer may choose a different grid, tilted or shifted or moving in another way, yet the underlying relations still have to be accounted for. That is why distance is more fundamental than the marks drawn to measure it. The distance between two nearby points is not just a number placed on paper. It expresses something about how one location is connected to another. In flat, ordinary geometry, the rules are familiar. Straight lines are the shortest paths. Parallel lines remain evenly separated. Triangles have angles that add in a predictable way. These rules are so natural in human experience that they can feel identical with space itself, but they are really statements about the geometry of space under certain conditions. Geometry is the study of relation within space, and physics eventually discovered that geometry cannot always be assumed in advance. A surface can be flat, like a calm sheet, or curved, like the surface of Earth. On a curved surface, the shortest path may not look straight when drawn on a flat map. Lines that begin parallel can drift together or apart. The lesson is not that everyday geometry is useless. It is that space has measurable properties, and those properties may matter physically. This becomes important long before the full idea of spacetime appears. Even in simple physics, space is known through operations rods, clocks, light signals, angles, motions, and repeated comparisons. A distance is not merely imagined. It is measured by laying one standard against another or by timing a signal that travels in a known way. A direction is not merely named. It is fixed by reference to other bodies, instruments, or stable patterns. This gives space a scientific character. It is not just where things seem to be. It is what can be tested through relations among things. The location of the moon is not an isolated fact floating by itself. It is known relative to Earth, to the Sun, to distant stars, and to the mathematical frame used by observers. The position of an electron in an atom is not known in the same straightforward way as the position of a pebble, and that difference already hints that space behaves differently at different scales of description. Still, the need for relation remains. Space becomes meaningful when positions can be compared. A world with only one object and no possible reference to anything else would make the idea of position strangely thin. It could not be said to be here rather than there in any ordinary sense, because here and there require some contrast. This was one of the old tensions in thinking about space. Is space an independent thing, existing by itself even if nothing occupies it? Or is it only the set of relations among objects classical physics leaned heavily toward independent space, while later physics brought relations back into the centre? The modern view does not reduce space to a simple illusion. Instead, it treats spatial structure as something that may be tied more deeply to matter, energy, fields, and measurement than everyday intuition suggests. Empty space, in modern physics, is not necessarily nothing. It can contain fields, it can carry radiation, it can have quantum properties, it can expand on cosmic scales. These later ideas would not make sense if space were only a hollow absence. They become possible because space is a physical concept with behavior that can be studied. Even before adding time, space already carries the quiet beginning of a larger transformation. It allows separation, but also connection. It lets objects be distinct, but also lets influence move between them. The space between Earth and the Sun is not a meaningless gap, because light crosses it, gravity acts across it, and particles stream through it. The space inside a room is not merely unused volume, because air fills it, sound travels through it, and motion is constrained by its dimensions. In every case, space helps define what can interact, how long a signal may take to arrive, and what path a body can follow. This is why the question of space cannot remain only philosophical. Once physics measures motion carefully, space becomes part of the rules that determine what motion means. A body does not merely have a position, it changes position along a path. A path has length, direction, and shape. If forces act, the path can curve. If no force acts in classical mechanics, the path tends towards straightness. These ideas appear simple, but they rely on a stable background geometry. They assume that the meaning of straight, near, far, and parallel is already settled. For everyday mechanics, that assumption is safe enough. For deeper physics, it becomes a place where old certainty begins to loosen. The structure of space is most clearly seen when ordinary intuition is asked to stretch. On Earth, up and down feel absolute, but they are local directions shaped by gravity and the planet's surface. Far from Earth, those directions lose their familiar meaning. East and west are useful only after a reference frame has been chosen. Even rest itself is not purely spatial, because to say that an object remains in the same place requires a decision about what counts as the same place over time. A person standing on Earth is at rest relative to the ground, moving relative to the sun, orbiting within the galaxy, and carried with the galaxy through a larger cosmic web. Space alone cannot settle all of these descriptions. It can provide positions, but positions become physical stories only when joined to motion, and motion already requires time. This does not make space less real. It makes it less isolated. Its meaning grows through measurement, relation, and change. By the end of this first step, space is no longer just quiet emptiness around matter. It is a structured field of possible positions and paths, a measurable order that gives objects separation and relation. It can be mapped, but it is not the map. It can seem flat, but its geometry may need to be tested. It can appear passive, but later physics will show that its properties cannot always be detached from matter and energy. Space begins as familiar reality and slowly becomes one of the least simple parts of it. The next difficulty is that no position, distance, or path can fully exist as a physical description unless change is also present, and change brings time into the same problem. Time appears at first to be even more familiar than space, because every ordinary experience seems to arrive in an order. A glass falls after it is released, a signal is received after it is sent, a star forms, burns, changes, and eventually leaves behind a remnant. These descriptions depend on time before any calculation begins, because without time there is no before, no after, no duration, and no change from one condition into another. In daily thought, time often feels like a universal flow that carries every event forward at the same rate. Physics begins more carefully. It treats time as the ordered measure of change, the quantity that allows a process to be compared with another process and placed in sequence. A clock is not valuable because it contains time as a substance. It is valuable because it repeats a physical behavior in a reliable way. The swing of a pendulum, the vibration of an atom, the rotation of Earth, and the orbit of a planet can all become measures of time if they provide a stable rhythm against which other changes are counted. This makes time both deeply familiar and scientifically difficult. It is known through change, yet it is also used to define change. The simplest clock is any process that can return to a similar state again and again. A pendulum moves from one side to the other. A quartz crystal vibrates under electrical influence. An atom shifts energy states in a way that can be measured with extraordinary precision. None of these devices escapes the physical world. Each one depends on matter, forces, temperature, motion, and environment. That fact matters because time in physics is never measured from outside the universe. It is measured by comparing one part of the universe with another. A second is not an abstract feeling of length. It is a defined duration based on a repeated physical process. This approach gives time a practical foundation. It allows laboratories in different places to compare results. spacecraft to navigate, signals to be synchronized, and predictions to be tested. Yet it also shows why time is not as simple as it seems. If every measurement of time depends on a physical clock, then the behavior of clocks becomes part of the question. A clock that moves quickly or sits in a different gravitational environment may not agree with another clock. That later result belongs to relativity, but the seed of it is already present in the act of measurement. Time is not just a number added to events. It is the condition that allows events to be ordered. In a physical description, an event has a location and a time. The location says where it occurs. The time says when it occurs relative to a chosen system of clocks. Without that temporal coordinate, a map of positions would be incomplete. A planet at one place in its orbit is not fully described unless the moment is known. A particle detected in a chamber does not have only a place of detection. It has a detection time, and that timing may be essential for reconstructing its path. Even a simple statement such as the light reaches the mirror becomes incomplete without sequence. The light leaves, travels, reflects, and returns. Time gives the ordering that turns separated facts into a process. This is why time is more than a label placed on change after the fact. It is built into the way cause and effect are described. A cause must be able to influence an effect only through allowed physical connections, and those connections require time to pass, even if the interval is extremely small. The link between time and causality is one of the strongest reasons it cannot be treated casually. Causality means that events are connected in an order where one event can help produce another. In ordinary experience, this order seems obvious. A match is struck before the flame appears. A sound is produced before it is heard at a distance. In physics, causality becomes stricter because no influence is known to travel faster than light in vacuum. This limit means that time is not only a measure of duration, it helps define which events can affect one another. If two events are too far apart in space and too close together in time, even light cannot cross the distance between them. They cannot be linked by a direct physical signal. This creates a deep structure in the ordering of the universe. Events are not merely earlier or later in some loose sense. Their separation in time and space determines whether influence is possible. This idea will become central in spacetime, but it begins with the need to understand time as the framework of sequence and possibility. There is also a difference between measured time and experienced time. Human awareness gives time a psychological texture. Some moments seem to pass slowly, while others seem to disappear quickly. Memory, attention, and biological rhythms shape that experience. Physics does not dismiss it, but it studies another question. It asks how time behaves as a measurable part of nature. A clock does not speed up because a person is bored, and it does not slow down because a person is afraid. Scientific time must be public, repeatable, and comparable. Yet the human sense of time reveals something important. Time is not perceived like space. A room can be examined in different directions, but the past is not available for inspection in the same way as the present. Records remain, memories remain, light from distant objects remains, but the earlier state itself is not simply waiting nearby. This gives time a direction in experience that space does not have. Physics calls this difficulty the arrow of time, a phrase that points to the observed fact that many processes have a preferred direction. A warm cup cools in a colder room. Broken glass does not gather itself back into an unbroken glass through ordinary motion. Smoke spreads through air rather than collecting back into a narrow stream. At the microscopic level, many basic laws of motion work almost the same forward and backward in time. The equations can often be reversed without obvious contradiction. Yet the large-scale world does not behave as if reversal is equally likely. The usual explanation involves entropy, a measure related to how many microscopic arrangements can produce the same large-scale condition. Systems naturally tend to move from more special, ordered arrangements toward more common, disordered arrangements, not because disorder is a force pulling them, but because there are vastly more ways for particles and energy to be spread out than carefully arranged. This gives physical time a direction connected to probability, heat, and information. The direction of time also matters in astronomy and cosmology. Light from a distant star carries information from the past because light needs time to travel. When a telescope records a galaxy far away, it does not show that galaxy as it is at the exact same cosmic moment by any simple everyday meaning. It shows light that left long ago. Looking outward in space becomes, in this limited observational sense, looking backward in time. This does not mean the telescope changes time or travels through it. It means that finite signal speed links distance to delay. The universe is therefore not observed all at once. It is reconstructed from signals arriving after different travel times. The sun is seen as it was a few minutes earlier. Nearby stars are seen as they were years earlier. Distant galaxies can be seen as they were when the universe itself was much younger. Time is built into observation so deeply that the sky is never a single present surface. It is an archive of arrival times, ordered by the paths that light has taken. Still, time cannot be reduced only to clocks, entropy, or memory. Each captures part of the concept, but not all of it. Clocks measure duration. Entropy helps explain direction. Memory stores traces of earlier states. Causality orders possible influence. None of these alone provides a complete final answer to what time is. This is part of the reason time remains one of the most difficult ideas in science. In some equations, time appears as a parameter, a value that marks how a system changes. In relativity, it becomes part of a larger geometry, joined with space. In attempts to understand quantum gravity, time becomes even more unsettled, because the usual background on which change occurs may no longer be available in the same way. But before reaching those deeper problems, the central lesson is already clear. Time is not simply a flowing container separate from events. It is the ordering principle by which change becomes measurable. Causes can precede effects. And physical histories can be described. A universe without time would not merely be frozen. The word frozen itself would lose meaning, because freezing implies a condition that persists. Persistence, motion, decay, growth, signal, rhythm, and memory all depend on temporal order. Space allows things to be apart. Time allows states to differ without being simultaneous in the same way. Together, they make physical description possible. The next step is to see why these two ideas, once treated as separate foundations, begin to merge as soon as motion and light are examined with enough care. The separation between space and time begins to fail when motion is measured with enough care. At low speeds, the older picture seems natural. Space gives the distance an object crosses, time gives the duration of the crossing, and speed is found by comparing the two. A person walking across a room, a train moving between stations, or a planet changing position against the stars can all be described this way with great success. Space and time appear to play different roles. Space is where the movement happens, and time is the measure of how long it takes. This distinction works so well in ordinary experience that it can seem built into reality itself. Yet the deeper laws of motion place pressure on that separation. The difficulty appears most clearly when observers are not all resting relative to one another. If one observer stands on a platform and another moves past on a train, both can describe the same physical event. But they do not assign the same spatial distances to every part of the situation. Each observer has a valid frame of reference, meaning a chosen way of measuring position and motion. Classical physics accepted this difference in spatial description while keeping time universal. The moving observer and the stationary observer could disagree about distances and speeds, but the same time was assumed to pass for both. That assumption was the hidden joint holding the older picture together. Light is the phenomenon that exposes the weakness in that joint. In everyday motion, speeds combine in a simple way. A ball thrown forward from a moving vehicle has a speed relative to the vehicle and a different speed relative to the ground. The ground observer adds the vehicle's motion to the ball's motion. This rule matches common experience, and for slow objects it is extremely accurate. Light does not follow that pattern. Careful experiments and the structure of electromagnetic theory show that light in vacuum has the same measured speed for every observer moving uniformly. No matter how the source or the observer moves, this is not a small technical detail. It changes the role of both distance and duration. If two observers are moving differently and both must measure the same speed of light, then they cannot always agree about the distance the light travels and the time it takes in the old way. Something that once seemed fixed has to adjust. The adjustment is not a flaw in measurement, it is a feature of nature. The speed of light becomes the stable quantity, and space and time become parts of a combined structure that different observers divide differently. The key point is that speed already joins space and time. It is distance measured per duration. If there were no relation between them, motion could not be described at all. But ordinary speeds do not force the relation to become obvious, because the corrections are far too small to notice. A car, a spacecraft, or even a planet moves much more slowly than light. In such cases, the older separation remains an excellent approximation. The clocks do not appear to disagree in any dramatic way, and lengths do not appear to change with motion. But as speeds approach a significant fraction of light speed, the hidden connection becomes measurable. A moving clock is found to tick more slowly relative to a clock at rest in the observer's frame. A moving object is measured to be shorter along the direction of motion. These effects are not caused by mechanical damage to the clock or physical compression of the object in the ordinary sense. They arise because space and time are not independent backgrounds. They are related aspects of one geometry, and different observers slice that geometry into spatial and temporal parts in different ways. This is where simultaneity becomes important in daily life. It seems reasonable to say that two distant events happen at the same time. A light turns on in one city, and another light turns on in another city. If the clocks in both cities show the same reading, the events are called simultaneous. But synchronization itself depends on signals, and signals take time to travel. When observers are moving relative to one another, the procedure for deciding what counts as the same time across separated locations does not produce a universal answer. Two events that are simultaneous for one observer may not be simultaneous for another observer moving at a different speed. This does not mean reality becomes confused or arbitrary. It means that simultaneity across distance is not absolute. It depends on the observer's state of motion. The events themselves remain real. Their ordering can be agreed upon when one can influence the other, because causality is protected by the light speed limit. But for events separated in such a way that neither can affect the other, different observers may legitimately disagree about which happened first. This result is one of the clearest reasons space and time must be joined. A purely spatial separation for one observer may include a temporal separation for another. The division between where and when is therefore not the same for everyone. What remains stable is the space-time relation between the events. This relation includes both their spatial distance and their time difference in a combined measure that all observers can agree on, even when they disagree about the separate pieces. The situation is similar in logic to describing a path from different angles, though the physics is more exact and less visual than any simple comparison can capture. One observer may assign more of the separation to space, Another may assign more to time, but the underlying interval remains the shared physical fact. The interval determines whether events can be causally connected, whether a signal moving at or below light speed can pass between them, and what kind of separation they possess. In this sense, space-time is not created by adding time onto space as an afterthought. It is the deeper structure from which the separate ideas of space and time are drawn by observers. The need for this structure was not invented to make physics more abstract. It emerged because experiments and equations demanded it. Electromagnetism had already shown that light behaves as a wave of electric and magnetic fields moving at a definite speed in vacuum. If that speed were measured differently by different observers in the classical way, the laws of electromagnetism would change from one uniformly moving frame to another. But nature does not appear to work that way. The same fundamental laws hold for observers moving uniformly relative to one another. Einstein's special relativity made this principle central and accepted the constancy of light speed as a foundation. The result was a new understanding of measurement itself. Length and duration are not discarded. They remain real measured quantities, but they are no longer universal in isolation. They depend on the frame of reference, space-time, rather than space alone or time alone, becomes the more reliable level of description. This also clarifies why everyday intuition resists the idea. Human senses evolved in a narrow range of speeds and gravitational conditions. In that range, space and time behave almost as if they are separate. The relativistic corrections are so tiny that they can be ignored for walking, building, throwing, sailing, and most ordinary engineering. A clock on a moving bicycle does not visibly fall behind a clock at rest. A ruler carried through a room does not seem shortened. The older picture feels natural because it is an excellent low-speed limit of a deeper theory. But physics is not limited to the range where human intuition was formed. Particle accelerators, atomic clocks, satellite navigation, and high-energy astronomy all operate in domains where the unity of space and time must be taken seriously. Fast particles live longer as measured in the laboratory than they would if time were absolute. Satellites require relativistic corrections because their motion and gravitational environment affect their clocks. These are not philosophical refinements. They are measurable consequences of the way the universe keeps order. Once space and time are joined, motion is no longer merely an object changing place as universal time passes. Motion becomes a path through space-time. An object at rest in space still moves through time. A fast-moving object changes the balance between its motion through space and its measured passage through time relative to another observer. This statement has to be handled carefully because it can be oversimplified. It does not mean an object chooses between space and time as if spending a supply of motion. It means that the geometry of space-time relates spatial motion and elapse proper time, the time measured by a clock travelling with the object. The faster an object moves through space relative to an observer, the less proper time elapses along that object's path between two shared events compared with the observer's own clock. This is why time dilation is not an illusion produced by bad instruments. It is a difference in the lengths of path through space-time, measured by clocks rather than rulers. The interlocking of space and time also protects causality. If time were absolute and signals could travel at any speed, cause and effect would be much harder to preserve. In relativity, the light speed limit gives space-time a causal structure. Around every event, there is a set of possible future events that can be reached by light or slower signals, and a set of possible past events that could have influenced it. Events outside those regions cannot be connected by any ordinary physical influence. This structure depends on both space and time together. A large spatial distance can be crossed only if enough time is available for a signal to travel. A short time interval can allow influence only across a limited distance. Causality is therefore not written in time alone, it is written in space-time. By the end of this step, the old separation has not been destroyed for practical life, but it has lost its claim to be fundamental. Space and time still appear as distinct aspects of experience, and they remain useful in calculation, navigation, and description. Yet the deeper theory shows that they are different projections of a single physical order. What one observer calls mostly distance, another may partly call duration. What one observer considers simultaneous, another may not. Beneath those differences, space-time preserves the relations that all observers can use. The next step is to see how this unified idea was born historically, as physics moved from separate absolute backgrounds toward a geometry where space and time became one structure. The birth of space-time did not happen because physicists wanted a more unusual language. It happened because the older language had become too narrow for the evidence. For a long time, the strongest working picture came from Newtonian mechanics, where space and time were treated as separate foundations. Space was the fixed arena in which bodies had positions, distances, and directions. Time was the universal measure that passed evenly everywhere, whether anything moved or not. This separation gave physics enormous power. It allowed the fall of an apple, the swing of a pendulum, the motion of the moon, and the paths of planets to be described within one mathematical system. The same framework helped engineers build machines, predict orbits, and understand ordinary motion with remarkable accuracy. Because it worked so well, it also felt natural. Yet its success depended on conditions where speeds were small compared with light and gravity was not extreme. Within that familiar range, space could appear independent, time could appear absolute, and the difference between them could remain hidden. The first cracks did not come from philosophy alone. They came from light, electricity, magnetism, and the problem of how the laws of physics should look to observers in motion. During the development of electromagnetic theory, light became understood as a disturbance involving electric and magnetic fields, moving in vacuum at a definite speed. That result raised a difficult question. If light was a wave, many physicists expected it to move through some underlying medium, often called the ether. If Earth moved through this medium, then the measured speed of light should vary slightly depending on the direction of motion through it. Experiments designed to detect such variation did not find the expected result. Light kept behaving as though its speed in vacuum was not tied to the motion of the observer in the ordinary way. At the same time, the equations of electromagnetism did not fit comfortably inside the older rules for adding velocities. The conflict was precise, not vague. Either the laws of electromagnetism change from one uniformly moving frame to another, or the old assumptions about space and time needed revision. Several mathematical pieces appeared before the full interpretation became clear. Hendrik Lorentz developed transformations that allowed the equations of electromagnetism to keep their form for moving observers. These transformations showed how measurements of length and time would have to change between frames moving relative to one another. At first, such changes could be treated as effects connected to motion through a hidden background. They looked like a way to save the older picture by adjusting matter, clocks, and rulers. What Einstein did was different. He removed the need for the hidden medium and placed two principles at the center. The laws of physics are the same for all observers moving uniformly, and the speed of light in vacuum is the same for all such observers. From those principles, the changes in measured length, time, and simultaneity were no longer patches added to the theory. They became the natural structure of measurement. Space and time were not fixed separately behind events. They were tied together by the way any observer could consistently measure light, motion, and causality. This was the beginning of special relativity. But the word spacetime had not yet taken its mature form. Einstein's theory showed that simultaneity is relative, that moving clocks are measured to run slow, and that moving lengths are measured to contract along the direction of motion. These results were already enough to undermine absolute space and absolute time. Still, they were often expressed as transformations between measurements. The deeper geometric meaning became clearer with Hermann Minkowski. Minkowski recognized that Einstein's theory could be written as a geometry in which space and time form a single four-dimensional structure. In this view, an event is not placed only somewhere in space and then separately assigned a time from outside. It is located in space-time. Different observers may divide the relation between events into different amounts of space and time, but they agree on a combined interval. That interval becomes the stable quantity beneath the changing descriptions. This was a major shift in understanding. The separate measurements could vary, while the space-time relation remained physically meaningful. Minkowski's insight did not make relativity less physical by making it more mathematical. It made the physical content clearer. Geometry had already been the language of space, but now geometry had to include time in a new way. This did not mean time became exactly the same as a spatial direction. Time has a different sign in the space-time interval, and that difference protects causal order. A person can turn around in space and move in another spatial direction, but ordinary matter does not move through time with the same freedom. The temporal dimension is joined to the spatial dimensions without losing its special causal role. The power of the four-dimensional view is that it shows why relativistic effects are not separate oddities. Time dilation, length contraction, and relativity of simultaneity become different consequences of the same structure. They are not unrelated surprises. They are ways that different observers slice one space-time into space and time. The change can be compared with rotating a coordinate system in ordinary geometry, but only in a limited mathematical sense, because space-time geometry is not the same as ordinary spatial geometry. The point is simpler and more important coordinates can change while the underlying relation remains. One observer may say that two events are separated by a certain distance and a certain time. Another, moving relative to the first, may give different values. If both use the rules of relativity correctly, they still agree on the space-time interval. This agreement is what gives the theory its stability. The real structure is not each observer's private division into space and time. The real structure is what remains consistent across all valid frames. The historical change was therefore not a rejection of Newton in the simple sense. Newtonian mechanics remains a powerful approximation. It still describes a large part of human-scale motion with extraordinary usefulness. The new theory showed where that approximation comes from and why it fails under certain conditions. When speeds are small compared with light, the equations of relativity reduce almost exactly to the older rules. Universal time and fixed space become excellent practical shortcuts. They are not fundamental, but they are not foolish. They are the low-speed shadow of a deeper geometry. This is one reason scientific revolutions are often subtler than a simple replacement of old by new. The older theory is preserved where it works, limited where it does not, and understood as part of a broader structure. Spacetime gave physicists a better language for the domain where light speed, high velocity, and precise timing could not be ignored. It also prepared the ground for a larger change still to come. Special relativity described spacetime as flat, meaning that it had a fixed geometry unaffected by gravity. Objects moved through this flat spacetime according to rules that linked space, time, energy, and momentum. But gravity still sat uneasily beside the theory. Newton had treated gravity as a force acting across space, pulling masses toward one another. Special relativity made such instant action unacceptable because influence could not travel faster than light. The question became sharper. If space and time were one structure, and if signals were limited by that structure, then gravity could no longer be described as though it crossed an absolute space instantly under an absolute time. The birth of spacetime therefore created a new problem as well as a new solution. It solved the conflict between uniform motion, light, and electromagnetism, but it made the older idea of gravity look incomplete. This is how a concept becomes more than a name. Spacetime was not merely a convenient combination of two words. It reorganized what counts as an objective fact. The position of an event, the timing of an event, and the distance between events could no longer be treated as separate final answers. They were frame-dependent pieces of a larger relation. The physical world became a network of events, intervals, world lines, and causal limits. The birth of space-time marked the point where physics stopped asking how objects move through space while time flows in the background, and began asking how histories are shaped inside a unified geometry. The next stage is to understand that geometry more directly, not as a phrase attached to relativity, but as a four-dimensional framework in which every physical event has its place. Four-dimensional reality is not an attempt to make the universe sound stranger than it is. It is the direct result of asking how an event can be located completely. To say where something happens, ordinary space requires three directions. A point may be left or right, forward or backward, higher or lower, depending on the chosen coordinate system. These directions allow position to be described with enough detail for everyday motion, astronomy, engineering, and laboratory work. Yet a position alone is never a complete physical event. A flash of light at a point in a room, a collision between particles, the arrival of a radio signal, or the passing of a planet across a telescope's field must also have a time. Without the time coordinate, the description is incomplete, because the same place can hold many different events at many different moments. Spacetime joins these requirements into a single framework. It does not erase the difference between space and time. It places them inside one structure, where the location of a happening includes three spatial coordinates and one temporal coordinate. This is what physicists mean when they speak of four-dimensional spacetime. The phrase can be misleading if it is treated as a hidden direction that ordinary perception has simply failed to notice. The temporal dimension is not another direction like north, east, or upward. It behaves differently, and its difference is central to causality. In ordinary space, movement can be turned around. A spacecraft can travel outward from Earth and later return. A particle can move left and then right. A person can climb and descend. Time does not enter experience with that same freedom. Physical histories have an order, and ordinary objects move along that order rather than wandering through it as they do through spatial directions. This is why space-time is not just space with an extra line attached. It is a geometry with a distinct temporal part. The difference appears mathematically in the way intervals are measured, but it can be understood in simple terms. Spatial separation can be crossed if enough time passes and a signal or object moves fast enough. Temporal separation helps decide whether that crossing can happen at all. Together they determine possible connection. The four-dimensional view becomes clearer when attention shifts from objects to events. An object seems to persist through time, but physics can describe that persistence as a chain of events. A planet is at one place at one time, at another place at a later time, and at still another place after that. The planet's history is the ordered collection of these space-time locations. In this sense, an object does not merely occupy space, it traces a path through space-time. That path is called a world line. A world line is not a visible trail left behind in space. It is a way of representing the complete history of an object as a sequence of events. For an object that remains at rest relative to a chosen frame, the spatial coordinates may stay the same while the time coordinate changes. For an object in motion, both spatial and temporal coordinates change. Either way, the object has a space-time history, not just a spatial position. This helps remove a common misunderstanding. Four-dimensional space-time does not require the human mind to picture a complete shape in the way it pictures a table or a planet. Scientific understanding often goes beyond direct visualization. A map of Earth can show a curved surface on flat paper, even though it distorts some relations. A graph can show temperature changing with time, even though temperature is not a direction in a room. In a similar way, space-time can be understood through relations, coordinates, intervals, and predictions, even when it cannot be imagined as a simple object. The need for 4 dimensions comes from measurement, not from visual intuition. Every event needs enough information to distinguish it from other events. 3 spatial coordinates distinguish where, 1 temporal coordinate distinguishes when. The combined set gives the event its place in space-time. Once this is accepted, the question becomes less about how to imagine 4 dimensions and more about what the structure does. The most important thing it does is preserve relations that different observers can agree on. In ordinary space, 2 people may choose different coordinate systems for the same room. One may measure from the door, another from the center of the floor. The coordinates assigned to a chair will differ, but the physical distance between nearby objects can still be translated between their descriptions. In space-time, different observers moving relative to one another assign different space and time coordinates to events. They may disagree about the duration between 2 events, the distance between them, or whether 2 separated events occur at the same time. Yet they agree on the space-time interval when it is calculated correctly. The interval is the combined separation that remains stable under the transformations of special relativity. It is the reason the theory does not dissolve into personal viewpoint. Measurements can differ, but not all things are negotiable. The underlying space-time relation remains fixed. This also explains why the temporal dimension cannot be treated as a casual addition. If time were simply another spatial direction, the causal structure of physics would not work in the observed way. In space-time, separations come in different kinds. Some events are separated so that a slower-than-light object or signal can travel from one to the other. These events can be causally related. Some are separated in such a way that only light could connect them. Others are too far apart in space and too close in time for any influence moving at or below light speed to pass between them. This classification depends on the full 4-dimensional separation, not on space alone and not on time alone. A distant explosion and a detector reading cannot be connected unless there is enough time for light or another signal to cross the distance. A nearby event may be connected with very little delay. The structure of space-time tells physics which histories are possible and which are excluded by the light speed limit. The 4-dimensional view also changes the meaning of rest. In ordinary thought, rest means not moving through space, but in space-time, an object at rest still has a history. Its world line continues from earlier events to later events. A clock sitting on a desk is not spatially travelling across the room, but it is measuring elapsed time along its own path through space-time. That elapsed time is called proper time, the time recorded by a clock that travels with the object. Proper time is especially important because it belongs to the path itself. 2 clocks that separate follow different space-time paths, and meet again may record different amounts of elapsed time. This is not because one clock has made a mistake. It is because their world lines through space-time have different lengths in the temporal sense. The idea is unusual only because everyday speeds are too small for the difference to stand out. At high speeds, it becomes measurable and unavoidable. In this framework, the present also becomes more subtle. Everyday life treats the present as a shared slice of the universe, a single moment extending everywhere. Four-dimensional space-time does not support that simple picture for all observers. A slice of simultaneity depends on the motion of the observer. Events that lie across a single present for one frame may belong to different times for another frame moving relative to it. This does not remove local experience. Nearby events can still be ordered with ordinary confidence. It does mean that a universal present, spread across all space in the same way for everyone, is not part of special relativity. The universe is better described as a network of events with causal relations, rather than as a series of universal instants stacked one after another. This is one reason the four-dimensional picture feels calm but radical. It changes the deep grammar of physical description without changing the familiar appearance of a room, a clock, or a moving hand. The value of four-dimensional space-time lies in its economy. Separate relativistic effects become connected. A moving clock runs slow relative to an observer because of how its world line is oriented through space-time. A moving ruler is measured shorter along its direction of motion because space and time coordinates transform together. Simultaneity changes because distant time assignments depend on the observer's frame. None of these effects has to be treated as an isolated trick. They are different expressions of the same structure. The deeper unity is not decorative. It reduces confusion by showing why the effects must occur together if the speed of light is to remain invariant, and the laws of physics are to remain consistent for uniformly moving observers. A four-dimensional framework is therefore not a luxury of advanced theory. It is the simplest coherent language for the world revealed by relativity. By the end of this step, space-time has become more than a merger of terms. It is the ordered setting in which every physical happening has both a place and a time. Every object has a world line, and every possible influence is constrained by the relation between distance and duration. Space still provides extension. Time still provides order. But neither stands alone as the final background. Their union forms the structure in which histories are drawn and causality is protected. The next step is to examine the smallest unit of that structure more closely, the event, the precise happening that gives space-time its points. An event in space-time is not an object, and it is not a long process spread out across a history. It is a precise happening, identified by where it occurs and when it occurs. A spark appears at the end of a wire. A photon reaches a detector. Two particles meet inside an accelerator. A radio pulse leaves an antenna on Earth. Each can be treated as an event if its location and time are specified closely enough for the question being asked. This simple idea gives space-time its working vocabulary. Instead of beginning with objects that endure, physics can begin with happenings that can be located. An object then becomes a sequence of events connected into a history. A planet at one moment in its orbit, the same planet later in another part of the orbit, and the same planet still later beyond that point form a chain. The chain is continuous in ordinary cases, but the individual event remains the basic mark. It is the point where the question of place and the question of time meet, without being separated into two independent stories. The usefulness of an event depends on coordinates, but coordinates should not be confused with reality itself. A coordinate system is a method for assigning values to events so they can be compared and calculated. In ordinary space, a chosen origin gives a starting point, and three directions give a way to locate position. One value may describe displacement in one direction, another value may describe displacement at a right angle to it, and a third may describe height or depth relative to the same frame. To locate a space-time event, a time value is added. The event is then described by 3 spatial coordinates and 1 temporal coordinate. This does not mean nature carries a visible grid. The grid is a human and mathematical tool. It allows different observers to organize the same physical situation. A laboratory may measure from the corner of a room. An astronomer may measure from Earth, the Sun, or the center of mass of a system. These choices can differ, but the event being described does not vanish when the coordinate system changes. The distinction matters because many confusions about spacetime come from treating coordinates as though they were physical objects. A map can place a city at a certain latitude and longitude, but the lines on the map are not carved into the ground. Spacetime coordinates work in a similar spirit, though with greater physical precision. They are useful because the relations among events can be translated from one valid system into another. If 2 observers choose different origins, or if one moves uniformly relative to the other, the coordinate numbers assigned to an event may change. The same flash of light may receive different spatial coordinates and a different time coordinate in each frame. That is not a contradiction. It is the expected result of describing one spacetime from different states of motion. What must remain consistent are the physical relations that the coordinates are meant to express. The interval between events, the causal order where influence is possible, and the reading of a clock along its own path have meanings that do not depend on a single preferred grid. The role of clocks is especially important because time coordinates are not assigned by feeling or assumption. To say when an event occurs in a frame, clocks have to be placed throughout that frame and synchronized by a defined procedure. In special relativity, synchronization is not trivial, because light needs time to travel, and its speed sets the standard for comparing distant clocks. A clock beside an event can record the local time directly, but if an event happens far away, its time must be inferred using signals and the rules of the chosen frame. This is why distance simultaneity is delicate. It is not enough to imagine one universal now covering all places. A network of clocks must be defined, and observers moving differently will build different networks of simultaneity. Each network can be internally consistent. None has the right to stand above all the others as the final temporal slicing of the universe. The event itself remains the meeting point of position and time, while simultaneity between separated events depends on the observer's motion. Spatial coordinates also require care. A distance measured between 2 events is not always the same as a distance measured between 2 objects at one time, because the phrase at one time already depends on simultaneity. When a ruler is at rest in one frame, its length can be measured by recording the positions of its ends at the same time in that frame. An observer moving relative to the ruler uses a different definition of same time across the ruler's length, and therefore obtains a different length along the direction of motion. The result is not a trick of perception. It follows from how spacetime coordinates are assigned. Measuring an extended object requires comparing separated events, and different frames disagree about which endpoint events belong to a single measurement. Once again, the object is not destroyed by the coordinate change. The description changes because the slicing of spacetime into space and time changes. An event avoids some of this ambiguity because it is local. It happens at one place and one time in a given frame. A single event does not have a length, and it does not require comparing distant positions at the same moment. This is why events are so clean as building blocks. They can be ordered, connected, and transformed between frames. When 2 events occur at the same location for a particular clock, the elapsed time between them on that clock is proper time. Another observer may assign different space and time coordinates to the same departure and arrival, but the clock's own elapsed time remains tied to its world line. In this way, local measurement gives space-time a firm anchor. The clock does not need to know the coordinate system of the universe. It records what happens along its own path, event by event. Causality gives events their deepest structure. Around any event in flat spacetime, possible influence is organized by light. Events that could be reached by a light signal form the boundary between what can be causally connected and what cannot. Events inside the future region can be affected by something moving at or below light speed from the original event. Events inside the past region could have affected it. Events outside these regions are separated in such a way that no ordinary signal can pass between them without exceeding light speed. This classification tells physics which stories are possible. A detector cannot register a pulse before the pulse has had time to arrive. A particle cannot influence another event outside its allowed causal reach. Different observers may disagree about the time order of events that cannot affect one another, but they will not disagree about the order of events where a real causal connection exists. The structure of spacetime protects this agreement. Coordinates also reveal how observation differs from occurrence. Seeing an event is itself another event. A star may explode far away, and the light from that explosion may reach a telescope much later. The explosion event and the detection event are connected by the path of light. The time when the explosion is observed is not the same as the time when it occurred in the chosen frame. The sky is not a direct display of one shared present. It is a collection of detection events on Earth or near Earth, each connected to earlier emission events by paths through space-time. The coordinate description allows those relations to be reconstructed. It separates the arrival of information from the event that produced it. Without that separation, distant observation would easily be mistaken for immediate knowledge. In general relativity, coordinates become even more flexible because space-time can be curved. There may be no single global coordinate grid that behaves simply everywhere. A local frame can still be chosen near an observer, and events can still be labelled. But the broader structure may require patches of coordinates, much as the curved surface of Earth requires more than one flat map to avoid distortion. The physical content lies not in any one coordinate choice, but in the relations that survive proper translation: curvature, proper time, causal connection, and the paths followed by freely falling objects carry the deeper meaning. A poorly chosen coordinate system can make a situation look singular, frozen, or distorted when the physical situation itself is regular. This does not make coordinates unimportant. It makes them tools that must be handled with discipline. By focusing on events and coordinates, space-time becomes less mysterious and more precise in another. It is not a hidden substance behind the world. It is the structured set of possible happenings and the measurable relations among them. Coordinates allow those happenings to be named from a chosen viewpoint. Transformations show how one valid description connects to another. Clocks and rulers supply local measurements. Light organizes causal reach. World lines connect events into histories. The central lesson is that a physical event is complete only when where and when are given together, and even then the numbers assigned to it depend on the frame used to describe it. What remains steady is the web of relations that no valid observer can simply choose away. The next step follows that web from isolated happenings into continuous motion, where matter does not merely occupy space-time but traces paths through it. Matter moves through space-time in a way that is more complete than the everyday phrase moving through space suggests. A stone crosses a room, a satellite circles Earth, a particle enters a detector, and each case appears at first to be a change of position as time passes. That description is useful, but it leaves the deeper structure hidden. In space-time, the moving body is not only found at a sequence of places, it occupies a sequence of events. At one event, the stone is near the hand that released it. At later events, it has different positions and different times. The continuous connection of those events is the body's world line. A world line is the history of an object written into space-time. It does not have to be visible as a mark in space. It is the ordered record of where and when the object exists, from one moment of its physical history to the next. Once motion is viewed this way, rest and movement become less absolute. An object resting on a laboratory table has a simple spatial description in the laboratory frame, because its position does not change much relative to the table, yet its world line still extends through time. It is not absent from space-time activity. It continues from earlier events to later events, and a clock resting beside it records elapsed proper time along the same path. A different observer moving past the laboratory assigns different coordinates to that same object in the moving frame, the table, the clock, and the object are all changing position. The object has not gained a second physical history. The two descriptions refer to the same world line, divided into space and time differently by different observers. This is the quiet power of space-time language. It separates what belongs to the object's history from what belongs to a chosen coordinate frame. Speed can then be understood as a relation between a world line and the observer's way of slicing space-time. In ordinary life, a slow object has a world line that leans only slightly away from the time direction of the observer's frame. A fast object has a world line more strongly tilted towards spatial change. The word tilted should not be taken as a visible angle in a room, but as a relation inside the geometry used to compare space and time coordinates. The faster the object moves through space relative to the observer, the less proper time elapses along that object's path between two shared events, compared with the time measured by the observer's own clock. This is the space-time meaning of time dilation. It is not caused by a clock struggling to keep up, and it is not a defect of machinery. It is a difference in the measured length of histories through space-time. The path taken by the clock determines how much time the clock itself records. This becomes clear in cases where two clocks separate and later meet again. If one clock remains close to Earth while another travels at high speed and returns, the two clocks can be brought together and compared at the same final event. They need not agree. The travelling clock may record less elapsed time. The difference is not a matter of opinion between observers after reunion, because the clocks are side by side and can be read locally. The explanation lies in their different world lines. They departed from the same event, followed different paths through space-time, and met again at the same event. Proper time depends on the path. In ordinary geometry, different paths between the same two places can have different lengths. In space-time, different histories between the same two events can contain different amounts of elapsed time. This comparison is limited, because space-time geometry has rules unlike ordinary spatial geometry, but it helps identify the important point. Time measured by a clock is not a universal flow added from outside. It is tied to the route the clock takes through space-time. The natural motion of matter is also shaped by the absence or presence of forces. In the older language of mechanics, an object with no force acting on it continues in a straight line at constant speed. In space-time, that statement becomes a claim about the object's world line. In flat space-time, a freely moving object follows the straightest possible path available to it, meaning an inertial world line. The object does not need a force to maintain this motion. Force is needed to change it, to bend the world line away from inertial motion. A rocket firing its engines, a charged particle deflected by a magnetic field, or a body pushed by contact forces all depart from the path they would otherwise follow. Acceleration is therefore not merely a change in speed through space, it is a change in the shape of the world line. An accelerometer carried with the object can detect this change locally, which gives acceleration a physical status different from steady relative velocity. One observer may say a spacecraft is moving fast, and another may say it is nearly at rest. But an accelerometer inside the spacecraft can reveal whether its engines are firing or whether it is drifting freely. This distinction matters because spacetime does not make all motion equivalent in the same way. Uniform motion can be described differently by different inertial observers without any one of them being the absolute rest frame. Acceleration, however, has direct physical effects. A passenger in a steadily moving spacecraft may feel no special force if the motion is uniform. A passenger in an accelerating spacecraft can feel pressure from the floor or seat because the path through spacetime is being forced away from free motion. In this way, spacetime preserves a careful balance. It removes the old idea of absolute rest, but it does not remove the difference between inertial and accelerated histories. The world line carries that difference. The shape of motion in spacetime becomes even more significant when light is included. Light does not have a rest frame in the ordinary sense, because it always moves at light speed in vacuum for all inertial observers. The path of a light signal through spacetime lies on the boundary of causal connection, often called a light-like path. Massive objects follow paths that remain inside this causal boundary, because they move slower than light. Events connected by such paths allow proper time to pass for the moving object. Light itself connects events with no proper time along its ideal path. Though care is needed because this does not mean light experiences anything, it means that the space-time interval along a light path has a special value. This special role of light organizes the possible motion of all matter and information. A world line for a massive body cannot cross outside the allowed causal region without requiring faster-than-light travel, which is not part of established physics. Motion through space-time is therefore constrained not only by forces, but by causal structure. Matter can follow many possible histories, but not every imagined history is physically allowed. A particle may curve under electromagnetic influence. A spacecraft may accelerate under engine thrust. A comet may follow a long gravitational path around the Sun, and a galaxy may move within the large-scale expansion of the universe. In each case, the motion can be described as a world line or a family of world lines. Extended objects require more than one line, because different parts of the object occupy different events. A rigid body is never perfectly rigid in relativity, because signals that transmit pushes and stresses cannot travel instantly through it. When one end of an object is moved, the other end cannot know immediately. The information travels through material at a finite speed. This is another place where spacetime change is an everyday assumption. Matter is not coordinated by a universal time acting everywhere at once. It is coordinated by local interactions traveling through spacetime. The motion of a body as a whole is built from countless local events linked by forces, signals, and internal structure. General relativity will later deepen this picture by showing that free motion in gravity is also motion along natural paths in curved spacetime. A falling object near Earth is not simply being pulled through a fixed background in the old sense. It follows a path shaped by the geometry around Earth, while the ground prevents nearby objects from following their own freefall paths. That fuller view belongs to the section on gravity, but the preparation is already here. Motion is not an object sliding through a passive container. It is a history within a structured set of possible relations. When spacetime is flat, the natural histories are straight in the relativistic sense. When spacetime is curved, the natural histories bend according to geometry. Forces, clocks, signals, and accelerations all become ways of reading the shape of those histories. By the end of this step, movement has changed meaning without losing its everyday usefulness. A thrown stone still crosses a room, a satellite still orbits Earth, a particle still arrives at a detector. But beneath those descriptions, each object traces a world line, and each clock measures proper time along its own path. Motion is no longer only change of place with time running behind it. It is the formation of a path through space-time, constrained by light, shaped by forces, and measured by the histories of clocks. The next step is to examine the special case where gravity is set aside and space-time remains flat, because in that simpler setting the strange clarity of special relativity can be seen most directly. Special relativity is the cleanest place to see why space-time is not only a philosophical idea, but a working structure of measurement. It begins by setting gravity aside. There are no curved paths caused by massive planets, no falling elevators, and no black holes. The setting is flat space-time, where observers moving at constant velocity can compare clocks, rulers, and light signals without the added complication of gravitational curvature. This does not make the theory small, it makes it precise. In this simpler arena, the old assumptions about space and time can be tested directly. The central rule is that the laws of physics have the same form for every inertial observer, meaning every observer who is not accelerating. A laboratory drifting smoothly through deep space and another moving uniformly relative to it must both be able to describe nature with the same basic laws. The second rule is more demanding. Light in vacuum has the same speed for all inertial observers. Once both rules are accepted, absolute space and absolute time cannot survive in their older form. The constancy of light speed is often the most difficult part to accept, because it disagrees with ordinary addition of speeds. If a vehicle moves forward and a ball's thrown from it, the ball's speed relative to the ground depends on both motions. Light does not behave that way. A beam sent forward from a moving spacecraft is still measured by an inertial observer to travel at the same light speed in vacuum. The spacecraft's motion does not simply add to the beam's speed. This does not happen because instruments are confused or because light has chosen a preferred observer. It happens because the measurement of distance and the measurement of time adjust together between frames of reference. Different observers do not agree on every spatial distance or every time interval, but they agree on the light speed and on the deeper space-time interval. The invariant quantity is no longer ordinary time or ordinary length by itself. It is the combined relation between events. This is why simultaneity changes first in the logic of special relativity. To decide whether two distant events happen at the same time, an observer must synchronize clocks across space. That synchronization depends on light signals and on the assumption that light travels at the same speed in opposite directions within the frame. For one inertial observer, two flashes at opposite ends of a moving train may occur simultaneously. For another observer moving with the train, the same two flashes may not be simultaneous. The difference comes from how each observer's network of clocks divides space-time into space and time. Neither observer is making a careless mistake. Each uses a consistent method inside a valid frame. What changes is the assignment of distant time. Local events remain straightforward. A single flash occurring beside a clock has a direct time reading for that clock. The difficulty appears when separated events are gathered into one claim about now. Special relativity shows that such a claim is not universal. Time dilation follows from the same structure. A moving clock is measured to tick more slowly relative to a clock at rest in the observer's frame. The effect is sometimes described as if the moving clock itself becomes sluggish, but that is not the best way to understand it. The clock may be functioning normally in its own frame, its own parts, chemical processes, vibrations, or atomic transitions proceed according to the same laws of physics. What differs is the relation between its world line and the observer's time coordinate. Between two events where the moving clock is compared with the observer's frame, less proper time may elapse along the moving clock's path. Proper time is the time measured by a clock travelling with the object. This means time dilation is not merely an appearance caused by delay in seeing the clock. After two clocks separate and later reunite, their readings can be directly compared, and the difference can be real. The effect is extremely small at everyday speeds, which is why ordinary life hides it. A person walking through a room does not carry a clock that visibly falls behind. A car on a road does not create a measurable human difference in aging. Yet the same principle becomes clear in high-speed particles and precise clocks. Particles produced in the upper atmosphere can reach Earth's surface in numbers that make sense only when their relativistic lifetimes are taken into account. Atomic clocks flown on aircraft or placed on satellites do not remain perfectly synchronized with clocks on the ground unless relativistic corrections are included. These examples matter because they show that special relativity is not a decorative theory attached to extreme imagination. It is part of the measured operation of the physical world. Flat spacetime may be abstract, but its consequences appear in instruments. Length contraction is the matching spatial effect. An object moving relative to an observer is measured to be shorter along the direction of motion. This does not mean the object feels squeezed in its own rest frame. In that frame, its ruler has its normal length. The contraction appears in another frame because measuring length requires recording the positions of both ends at the same time in that frame. Since simultaneity depends on the observer's motion, the events used to measure the two ends are not the same events that another frame would choose. The disagreement over length is therefore tied directly to the disagreement over simultaneity. It is not a separate physical damage done to the object. It is a consequence of how space-time is divided into spatial slices by different observers across the direction of motion. No such contraction occurs in special relativity. The change belongs specifically to the line of relative motion. These effects do not appear independently. They are bound together by the Lorentz transformations, the mathematical rules that connect the space-time coordinates assigned by one inertial frame to those assigned by another. The transformations replace the older Galilean rules that worked well at low speeds, at slow speeds. The Lorentz transformations become almost identical to the older rules, which explains why Newtonian intuition works so well in daily life. Near light speed, the difference grows. Time intervals, lengths, and simultaneity shift in ways that preserve the speed of light and the space-time interval. This is the discipline behind the theory. It does not allow each observer to invent a private universe. It gives exact rules for translating between observers, and those rules protect agreement on the quantities that must be shared. Energy and momentum also change in this framework. As an object with mass is accelerated closer to light speed, more and more energy is required for further increases in speed. The object never reaches light speed through ordinary acceleration. Light speed is not merely a difficult speed for matter. It is the boundary that separates the possible paths of massive objects from the light-like paths of massless radiation in flat space-time. This boundary helps preserve causality. If signals could move faster than light, different inertial observers could disagree about causal order in ways that would allow effects to appear before their causes in some frames. Special relativity avoids this by giving space-time a stable causal structure. Events that can influence one another remain ordered consistently. Events too far apart to exchange a light signal may have frame-dependent time order, but they cannot be causally connected by any known physical process. The calmness of special relativity comes from this hidden order. Its results feel strange only when space and time are expected to behave as separate absolutes. Once space-time is accepted as the deeper structure, the effects begin to fit together. A clock's rate, a ruler's length, and a distant claim of simultaneity are not isolated facts floating above motion. They are measurements made within frames. Different inertial frames are equally valid, but their measurements must be related by precise rules. The invariant speed of light is the thread that forces those rules into place, and the space-time interval is the shared relation that remains when coordinates change. Flat spacetime, therefore, does not remove reality. It clarifies which parts of measurement belong to perspective and which parts belong to structure. By the end of special relativity, the universe has become less absolute in its surface descriptions and more unified underneath. Space alone is not the fixed stage. Time alone is not the universal clock. Together they form flat spacetime, where inertial motion, light, causality, and measurement obey one coherent geometry. This geometry explains why moving clocks slow relative to observers, why moving lengths contract along motion, why simultaneity across distance is frame-dependent, and why no massive object can be accelerated to light speed. Yet gravity has still not entered the picture. The next step is therefore unavoidable, because matter and energy do not merely move through space-time. In the presence of gravity, they help determine its shape. General relativity begins with the difficulty left behind by special relativity. Flat space-time explains motion, light, simultaneity, and causality when gravity is absent or weak enough to ignore. But the universe is not built without gravity. Planets orbit stars. Stars gather into galaxies. Light bends near massive bodies. Clocks run at different rates depending on gravitational environment. The older Newtonian picture described gravity as a force pulling masses across space, with time passing in the same way everywhere. That picture remains accurate for many ordinary calculations, yet it sits uneasily beside the idea that no influence can travel faster than light. If gravity were an instant pull across fixed space, then a change in one mass would be felt everywhere at once. Relativity does not allow that. The deeper answer is not to make gravity faster or to hide the delay. It is to change what gravity means. In general relativity, gravity is not primarily a force acting through space-time. It is the shape of space-time itself, and freely falling matter follows the natural paths allowed by that shape. The starting point is the equivalence between gravity and acceleration. A person standing on the ground feels weight because the ground prevents free fall. A person in a falling elevator, neglecting air resistance and danger, would feel weightless for a short time because everything nearby follows almost the same falling path. This does not mean gravity has disappeared. It means that locally, over a small enough region, free fall can remove the felt effect of gravity. Einstein recognized that this was more than a curious fact. It suggested that gravity might not be an ordinary force at all. If freely falling objects do not feel forced, perhaps they are following the straightest available paths in a space-time that is not flat. The ground, by resisting that natural path, produces the sensation of weight. This reverses the usual intuition. A falling object near Earth is not being pushed by a mysterious pull in the same basic way a hand pushes a stone. It is moving along a path shaped by space-time geometry, while the surface of Earth blocks such motion and creates pressure upward. To understand this, curvature has to be treated carefully. Curved space-time does not mean that space alone bends into some surrounding higher room that must be seen from outside. It means that the relations among events, distances, durations, and paths differ from the relations expected in flat space-time. Curvature is intrinsic. It can be measured from within the system. In ordinary geometry, one can detect curvature on Earth by measuring large triangles or by comparing paths over the surface. In general relativity, curvature is detected through the behavior of clocks, light, and freely falling bodies. Nearby falling objects may drift together or apart even when no engine or contact force acts between them. This relative acceleration is a sign of tidal gravity, and tidal gravity is the local evidence of space-time curvature. A small freely falling laboratory may resemble an inertial frame for a brief time, but a larger region cannot hide the curvature completely. The paths of separate objects reveal it. Matter and energy are what determine this curvature. General relativity does not say only that mass pulls on mass, it says that energy, momentum, pressure, and stress contribute to the geometry of space-time. The physical meaning can be stated without writing the field equations down. The contents of the universe influence the structure of space-time, and that structure influences how the contents move. This is a coupled relationship. A star shapes the space-time around it, and planets follow paths through that curved geometry. The planets also contribute their own small curvature, a galaxy, a cluster of galaxies. And the universe as a whole each have space-time structure connected to their matter and energy content. Gravity becomes geometry in motion with matter, not a separate invisible thread stretched through a passive background. The orbit of Earth around the Sun illustrates the change in language. In Newtonian physics, the Sun exerts a gravitational force on Earth, constantly bending its motion away from a straight line. In general relativity, Earth follows a geodesic, a natural path through curved space-time, near the Sun. This does not mean the orbit is merely an illusion, and it does not make the Newtonian description useless. The older force picture remains an excellent approximation for the solar system in many circumstances, but the geometric picture explains details the older view cannot fully capture, such as the small extra shift in Mercury's orbit. Mercury moves close enough to the Sun and fast enough that space-time curvature produces a measurable correction to its path. The success of general relativity in explaining the correction showed that curved space-time was not only an elegant idea, it answered a real astronomical discrepancy. Light also follows the geometry. Since light has no rest mass, the older phrase gravitational attraction of light can be misleading if taken too simply. General relativity explains the bending of light as motion, along paths shaped by curved space-time. Starlight passing near the Sun is deflected slightly. Light passing near a galaxy or cluster can be bent more strongly, sometimes producing gravitational lensing, where distant objects appear distorted, magnified, or repeated. Lensing is now one of the practical tools of astronomy. It helps reveal mass that may not shine, including dark matter inferred from its gravitational effects. The important lesson is that space-time curvature affects not only heavy objects, but the routes by which information travels. Gravity changes the connection between events, and light carries that change into observation. Clocks reveal the same structure in a different way. In general relativity, a clock deeper in a gravitational field runs more slowly relative to a clock higher up, after the comparison is properly made. This is gravitational time dilation. It is not a weakness in the clock. It is a difference in proper time along different paths through curved space-time. Clocks on satellites and clocks on Earth do not tick at exactly the same rate, because they differ both in speed and in gravitational environment. Practical navigation systems must account for these effects. The fact that such corrections matter in technology shows again that space-time curvature is not a remote abstraction reserved for black holes. It reaches into precision timing around Earth. Gravity changes time, and once time is part of space-time, that statement becomes one expression of geometry. General relativity also changes the meaning of a gravitational field itself. In Newtonian physics, a field can be imagined as a value assigned across space, telling how strongly gravity pulls at each point. In general relativity, the field is the space-time geometry. There is no need for a separate gravitational force acting on a freely falling object. The object follows the local geometry unless another force pushes it away from free fall. This is why astronauts in orbit feel weightless, even though Earth's gravity remains strong enough to keep the spacecraft circling the planet. They are not beyond gravity. They are in continuous free fall, following paths around Earth. The floor does not press upward in the usual way, so the familiar sensation of weight disappears. General relativity makes that distinction clear by treating free fall as natural motion rather than forced motion. The theory becomes most demanding where curvature is intense. Near a black hole, space-time is curved so strongly that there is a boundary called the event horizon. Once inside that boundary, every future directed path for matter and light leads deeper inward. The horizon is not a material surface. It is a causal boundary in space-time. Outside observers cannot receive signals from events inside it, because those signals cannot find a future path outward. This makes black holes less like ordinary objects with surfaces and more like regions where causal structure has changed profoundly. General relativity predicts them as consequences of enough mass compressed into a small enough region. Observations of stellar motion, accreting gas, gravitational waves, and horizon-scale imaging all support the reality of black holes as physical systems. On the largest scale, general relativity becomes cosmology. If space-time is shaped by matter and energy, then the universe as a whole can evolve. Space itself can expand, changing the distances between galaxies that are not locally bound together. This expansion is not well described as galaxies flying through a pre-existing emptiness from a central point. It is better understood as a change in the large-scale geometry of space-time. Light travelling across this changing geometry is stretched, producing the cosmological redshift observed from distant galaxies. The same framework allows scientists to describe an early hot dense universe, the formation of structure, and the influence of dark energy on cosmic acceleration. These ideas do not answer every question, but they show how general relativity gives gravity a role in the history of the universe itself. Space-time is no longer only the setting for motion, it becomes part of the evolving physical system. By the end of this step, gravity has changed from a pull across space into a statement about geometry, motion, and time. Matter and energy shape space-time. Freely falling bodies follow its natural paths. Light bends because the roots of space-time bend. Clocks differ because proper time depends on position, motion, and curvature. Black holes reveal causal boundaries, and cosmic expansion shows that the geometry of the universe can evolve. The next step is to move toward the regimes where this structure is tested most strongly, where space-time is stretched by collapse, waves, horizons, and the expansion of the cosmos. Extreme space-time appears wherever the ordinary assumptions of distance, duration, and gravity are pushed beyond the calm conditions of daily life. Near Earth, curvature is weak enough that clocks, rulers, and falling objects still seem to behave almost classically. Around the Sun, the curvature is stronger, but still gentle enough that planets follow stable orbits and light bends by small amounts. The deeper tests begin where matter is compressed, where objects move rapidly, where gravitational fields change violently, or where the universe is considered as a whole. These are not separate exceptions to the theory. They are places where space-time reveals features that are usually hidden by familiar scale. A black hole, a passing gravitational wave, a pair of merging neutron stars, and the expansion of cosmic space all belong to the same larger question. They ask how geometry behaves when it is no longer a quiet background approximation, but part of the most active physics in the system. A black hole is the clearest example of space-time becoming a causal boundary. It forms when mass is compressed so tightly that escape from a certain region would require motion faster than light. The event horizon marks the boundary of that region. It is not a solid surface, and an observer falling through a large enough horizon might not notice a sharp local wall at the crossing. What changes is the future. Outside the horizon, light can still move outward if it is aimed properly. Inside the horizon, all future directed paths lead deeper inward. This is not because light becomes weaker, or because space behaves like a material trap. It is because the space-time geometry is arranged so the outward escape is no longer among the possible future paths. The horizon is therefore a statement about causality. It separates events that can send signals to the outside universe from events that cannot. The center of the ideal black hole brings a harder issue. General relativity predicts that collapse may lead to a singularity, a region where the mathematical description produces infinite density or curvature. Most physicists do not treat this as a simple physical object with infinite values that must literally exist as written. Instead, a singularity is widely understood as a sign that the theory has reached the edge of its domain. General relativity describes gravity and space-time extremely well on large scales, but it does not include quantum effects in a complete way. Near the deepest interior of a black hole, where curvature becomes extreme and matter is forced into conditions far beyond known laboratory experience, quantum gravity is expected to matter. The singularity is therefore not only a prediction of collapse, it is also a warning that the current theory is incomplete at its most concentrated limit. Black holes also create a problem involving information. In ordinary quantum theory, information about the state of a system is not simply destroyed. In black hole physics, however, matter and radiation can fall past the horizon and become inaccessible to outside observers. At the same time, black holes are expected to emit a very faint thermal radiation through quantum effects near the horizon. If a black hole slowly loses mass and eventually evaporates, the question becomes, what happens to the information about everything that fell in? Does it escape in a subtle encoded form, remain in some remnant, or require a change in how space-time and quantum theory are understood together? This is not a small technical puzzle. It connects horizons, thermodynamics, quantum mechanics, and the meaning of locality. It suggests that space-time may have microscopic rules that are not visible in general relativity alone. Gravitational waves test space-time in another way. They are ripples in curvature produced when massive objects accelerate in changing. Asymmetric patterns. A perfectly steady spherical mass does not send out gravitational waves merely by existing. Strong waves come from systems such as orbiting black holes or neutron stars, where enormous masses move rapidly and the gravitational field changes with time. When such waves pass through a detector, they slightly stretch and squeeze distances in perpendicular directions. The effect is extraordinarily small by the time it reaches Earth, but it carries direct information about the motion of space-time curvature far away. The first detections of gravitational waves confirmed a major prediction of general relativity and opened a new form of astronomy. Instead of observing only light, particles, or electromagnetic radiation, scientists can now observe the changing geometry produced by some of the universe's most compact systems. The merger of black holes is especially revealing because it is not a collision of surfaces. Two horizons orbit, lose energy through gravitational waves, draw closer, and eventually settle into a single larger black hole. During the final moments, space-time is not gently curved, it is dynamic, strongly nonlinear, and changing too quickly for simple approximations. Numerical relativity, which solves Einstein's equations with powerful computation, is needed to predict the wave pattern. The signal recorded on Earth carries phases a gradual increase as the objects spiral together, a peak as they merge, and a fading vibration as the final black hole settles. This last fading is called ring down. It is important because the final object should behave like a black hole described by only a few properties, such as mass, spin, and electric charge, though astrophysical black holes are expected to have almost no net charge. Testing that simplicity helps test whether the observed objects match the black holes predicted by general relativity. Neutron stars bring a different kind of extremity. They are not black holes, but they are dense enough that gravity, nuclear physics, and spacetime curvature meet in a narrow region of uncertainty. A neutron star contains more mass than the Sun compressed into a sphere only a few tens of kilometers across. Its matter is denser than atomic nuclei in many regions, and its internal state is not fully known. When two neutron stars merge, gravitational waves reveal their masses and motion, while light from the explosion can reveal heavy elements created in the aftermath. Such events connect space-time dynamics with the origin of elements like gold and platinum. They also help measure how stiff or soft neutron star matter may be under extreme pressure. In this way, space-time is not only a stage for compact objects, it becomes part of the instrument through which the properties of matter are inferred. Cosmic expansion tests space-time at the larger scale. In general relativity, the universe does not need to be static. The distances between galaxies can grow because the large-scale geometry changes over time. This expansion does not have a central point in ordinary space. It is a feature of the universe's overall metric, the rule that determines distances and times across the cosmic structure. The expansion rate has changed over cosmic history, influenced by radiation, matter, dark matter, and dark energy. Observations show that the expansion is currently accelerating, and the simplest explanation is dark energy, often described as a property of space itself or as a cosmological constant. Yet the physical nature of dark energy remains unclear. It may be a constant energy density associated with space-time, or it may point toward a deeper field or modification of gravity. The observation is firm. The explanation is still open. The early universe presses even harder on these questions. As the cosmic history is traced backward, the universe becomes hotter, denser, and more uniform. General relativity, combined with observed expansion, points toward an early state where densities and temperatures were extremely high. The phrase Big Bang does not describe an explosion into empty space. It describes the early hot, dense expansion of space itself. But when the equations are pushed all the way back, they again approach a singular boundary, where the known theory no longer gives a complete description. Quantum effects should dominate at such scales, and a final account would require a theory in which space-time itself can be treated quantum mechanically. Whether the earliest universe began from a true beginning, a bounce, a quantum transition, or something not yet well described remains unsettled. Extreme space-time therefore teaches two lessons at once. General relativity is extraordinarily successful because it predicts horizons, gravitational waves, lensing, time dilation, orbital corrections, and cosmic expansion with remarkable power. At the same time, the same theory points toward places where it cannot be the last word. Black hole interiors, the information problem, the earliest universe, dark energy, and the quantum structure of geometry all press beyond its completed form. These limits do not weaken the achievement. They show where the achievement becomes precise enough to reveal its own boundary. Space-time is tested most strongly where it bends, changes, traps, signals, carries waves, and expands across cosmic history. In those regimes, it remains a working physical structure, but it also begins to look less final than it once seemed. The next step is to examine that unfinished nature directly, where science asks whether space-time is fundamental or whether it may emerge from deeper rules not yet fully understood. The unfinished nature of space-time appears most clearly where the two great languages of modern physics do not yet fit together. General relativity treats spacetime as a smooth geometry, able to curve under the presence of matter and energy, and able to guide the motion of planets, light, stars, and galaxies. Quantum theory treats the microscopic world in a different way, through probabilities, fields, uncertainty, and discrete exchanges of energy. Each language is extraordinarily successful in its own domain. The difficulty is that the deepest conditions in nature do not respect that division. Inside the earliest moments of the universe, near the centre of a black hole, or at distances so small that ordinary geometry may lose meaning. Gravity and quantum behaviour have to belong to the same description. At that boundary, space-time can no longer be assumed to be a smooth background. It becomes part of the question. The issue is not simply that scientists lack enough data. The problem is conceptual. Quantum fields are usually described as living in space-time. They fluctuate, interact, and carry particles within a structure of position and time. General relativity says that this structure is not fixed, because matter and energy help shape it. When both ideas are taken seriously, the background becomes dynamic and quantum at once. A quantum field cannot simply live on a space-time that is already settled if space-time itself must also obey quantum rules. This creates a circular difficulty. The stage on which quantum physics is usually written may be one of the actors. A complete theory of quantum gravity would need to explain how geometry behaves when it is no longer smooth, certain, or independent of the systems it contains. Several approaches try to reach that deeper level, though none has yet become a confirmed final theory. String theory suggests that the basic objects of nature may not be point particles but tiny extended structures, with gravity emerging naturally through one of their possible vibrational states. Loop quantum gravity takes a different path, treating geometry itself as something that may have a discrete structure, with areas and volumes built from more basic quantum relationships. Other ideas explore causal sets, holography, quantum information, emergent space-time, or connections between entanglement and geometry. These approaches differ widely, but they share a central pressure. They all ask whether space-time is fundamental in the way everyday thought assumes, or whether it is a large-scale approximation that appears only after deeper ingredients are organized in the right way. The idea that space-time may be emergent is especially important. Emergence means that a familiar property appears from the collective behavior of more basic parts, even though it is not obvious in each part alone. Temperature is an example from ordinary physics. A single molecule does not have temperature in the same sense that a gas does, but the gas as a whole does. In a similar spirit, space-time might arise from underlying quantum relations that are not themselves spatial or temporal in the usual way. This possibility is difficult because it asks physics to explain the origin of the very framework used to explain origins. If space and time emerge, then the question before space-time cannot be asked in the ordinary temporal sense. It must be reformulated in terms of a deeper order that produces temporal behavior only under certain conditions. Black holes continue to guide this search because they join gravity, thermodynamics, and quantum theory in one physical system. A black hole has an event horizon with an area, and theory connects that area to entropy. Entropy is usually related to the number of microscopic arrangements behind a large-scale condition. If a black hole has entropy, then it seems to have microscopic degrees of freedom. Even if general relativity describes the horizon as a smooth geometric boundary, this suggests that space-time geometry may hide a deeper count of states. The black hole information problem sharpens the same point. If information is preserved in quantum theory, then the evaporation of a black hole cannot be described as simple thermal loss, with no memory of what formed it. Somehow, the horizon, radiation, and interior must fit into a more complete account. The answer may reveal that locality, the idea that objects interact only through nearby points in spacetime, is not as absolute as it appears. The holographic principle gives one of the most striking hints. It suggests that the information inside a volume of space may be related to information described on its boundary, rather than stored independently at every point within the volume. In certain mathematical settings, a theory with gravity in one kind of spacetime can be equivalent to a theory without gravity on a lower dimensional boundary. This does not mean ordinary space is a simple illusion. It means that the same physics may be expressible in a form where spacetime geometry is not the starting point, but something reconstructed from more basic information. Such results are not yet a complete description of the universe humans inhabit, but they have changed the question. Spacetime may be deeply connected to information, entropy, and entanglement, not only to distance and duration. Entanglement is another clue. In quantum theory, entangled systems have correlations that cannot be explained as if each part carries an independent, complete description. These correlations do not allow faster-than-light signaling, but they reveal that the quantum world is not built from simple separated pieces in the classical way. Some modern research suggests that patterns of entanglement may help build the connectivity of space itself. In this view, what appears as geometric closeness may reflect a deeper web of quantum relationships. The proposal remains incomplete, and it should not be treated as settled fact. Its importance is that it changes the direction of thought. Instead of asking only how particles behave within spacetime, physics begins asking whether spacetime is a way of organizing quantum connections that are more basic than location. Time may be even harder than space. In general relativity, time is flexible and local, measured along world lines and affected by motion and gravity. In quantum theory, time often appears as an external parameter, a background value against which quantum states change. Combining these roles is difficult. Some approaches to quantum gravity produce equations in which time does not appear in the ordinary way at the deepest level, if that is correct. The flow of time may also be emergent, tied to change, records, thermodynamics, or the perspective of observers within the universe. This does not mean time is unreal in the world of experience. It means that the time measured by clocks may not be a basic ingredient in the most fundamental description. Like smooth space, it may be a large-scale feature produced from deeper order. The expansion of the universe adds another unfinished question. General relativity describes cosmic history with great success, but the observed acceleration of expansion is usually attributed to dark energy, whose nature remains unknown. If dark energy is a cosmological constant, it may be a fixed energy density associated with spacetime itself, yet attempts to connect that value with quantum vacuum energy lead to severe theoretical tension. If dark energy is not constant, then it may reflect a field or a modification of gravity on large scales. Either way, the accelerating universe suggests that spacetime has properties still not understood at a basic level. The larger scale behavior of the cosmos and the smaller scale structure of quantum gravity may be linked by questions that current theories cannot fully close. Even the smoothness of spacetime is uncertain at the smallest distances. General relativity assumes that spacetime can be divided without limit, with positions and intervals defined as precisely as needed. Quantum theory and gravity together suggest that this assumption may fail near the Planck scale, a scale so small that direct experimental access is far beyond current technology. At such scales, fluctuations in geometry might become important, or the concept of a sharply defined point may lose its usual meaning. This remains speculative, because no experiment has directly revealed the microscopic grain of spacetime, if such a grain exists. Still, the possibility matters. A smooth geometry may be like a calm surface seen from far away, while the deeper structure, if it exists, follows rules not yet known. The unfinished nature of space-time is therefore not a gap at the edge of an otherwise simple idea. It runs through the centre of modern physics. Space began as the order of position and relation. Time began as the order of change and causality. Relativity joined them into a four-dimensional structure. General relativity made that structure dynamic, curved by matter and energy. Extreme systems then revealed horizons, waves, singularities, and cosmic expansion. The remaining question is whether space-time is the final arena of physics or a derived form of something deeper. Science does not yet know. What it has is a set of clues: black hole entropy, quantum entanglement, gravitational waves, cosmic acceleration, and the unresolved meeting point of general relativity with quantum theory. Together they suggest that space-time is both one of the most successful ideas ever developed and one of the least finished. Its familiar surface allows clocks to tick, light to travel, planets to orbit, and histories to unfold. Its deeper nature remains open, waiting for a theory that can explain not only how things move within space-time, but why space-time exists in the form that it does. The subject returns, at last, to a quiet balance. Space is no longer only distance, and time is no longer only duration. Together they form the measured order in which events can happen, signals can travel, clocks can differ, and histories can take shape. The idea begins in familiar experience, with position, motion, sequence, and change, then slowly widens until the familiar world becomes part of a deeper structure. In that structure, light sets the boundary of influence. Motion changes the comparison of clocks and rulers. Gravity becomes curvature, and the universe itself can expand. None of this removes the ordinary world. A stone still falls, a planet still orbits, a clock still ticks, and light still crosses the darkness between stars. What changes is the level at which these facts are understood. The background is no longer passive. The geometry is part of the physics. Still, space-time has not become a closed answer. At its strongest limits, near horizons, near the earliest universe, and perhaps at scales far below direct measurement, the smooth structure begins to point beyond itself. There may be deeper rules beneath distance and duration, rules connected to quantum information, entropy, fields, or forms of order not yet named with certainty. Science has not reached that final layer. It has only traced the edges carefully enough to know that the question remains real. Space-time is therefore both a foundation and an unfinished clue. It holds together the motion of galaxies and the ticking of clocks, yet it may itself arise from something quieter and more fundamental. For now, the known universe continues to be read through its events, its paths, its signals, and its curving geometry, while the deeper origin of that geometry remains open, patient, and still unresolved.